Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. And what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but they will apply a lot of the same principles apply over in the UK as well. Now, if you do have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring live chat. If you're watching this after the premiere, then just feel free to leave a comment underneath the video and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on's diagnostic technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had 30 different franchisees I worked with, as well as the shops that they serviced, in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru. So I worked in a dealership, and over time, I guess, just became the default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my bed. Then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So today we are talking about continuing our component testing series we've been doing. And we're going to talk about cooling system electronics. And you might think, oh, coolant system electronics. What do we have for cooling system electronics? Might not be a whole lot of diagnostic merit there, but according to newer cars today, there's a lot going on when it comes to cooling systems. So we have our usual standby engine coolant temperature sensor, right? That's been around for a very, very long time, having the coolant temperature sensor, being able to control the fans and so on and so forth, and letting the computer know what the temperature is. Also, some vehicles might use a cylinder head temperature sensor. That would be a very similar way of doing things, except it's measuring the temperature of the actual cylinder head. It could be a radiator outlet temperature sensor. Any of the temperature sensors, by and large, on the vehicle are going to be what we call a negative temperature coefficient thermistor. Right, so the resistance on the unit will change as the temperature changes. So we'll talk about those. We'll also talk about the thermostat, right? We have our old standby dumb thermostats, if you want to call them that. Just they have no electronics involved at all, but we have some of the newer cars, and I say newer, really it's 7, 8 years at least they've been using that. There's electronic thermostats on cars now. We'll talk a little bit about that. How about the cooling fans? Right, cooling fans aren't nearly as simple as they used to be either, because sometimes we have control modules dealing with those. And then we also have the active grill shutters, which are supposed to help increase aerodynamic efficiency and also change the temperature going into the air going in through the radiator, right? So that is considered part of the cooling system. And then, of course, we have electric water pumps. Now, we're used to having the mechanically driven water pumps, but there are many models out there now that are electric water pumps. And there's some vehicles that have both a mechanical and an electrical water pump that runs after the vehicle shuts down. So we need to be able to test these things and check these things, and awful lot of them will set codes, right? So we need to be able to go through the diagnostic flow with these things. So when we think about testing these, we're going to be thinking about component failures on them, right? So we could have one of 3 ways my component can fail. So we could have our opens. So that means I have no voltage getting to the component if I have open on the voltage feed, so that it's not getting voltage to the sensor, or I'm getting voltage to the sensor and sensor's not getting back to the computer, right? So that could be our no voltage from the component. Maybe it's coming out the component itself, but it's not making it all the way down on a wire back to where it needs to go back to the PCM. Maybe you have it open somewhere in the harness. How about a short? Right, so a short could be excessive voltage if I have a short to power. So say I'm only supposed to be 5 volts and it's rubbing against another wire in the harness and it's a 12-volt wire. So now I'm getting 12 volts into this 5-volt circuit. So that's never good. And that can cause an overvoltage situation. Or I could have insufficient voltage, right? If I have a short to ground, maybe it's chafing on a piece of metal on the engine or something of that nature, and it's just momentarily shorting the ground. That'll pull that voltage away, and then I won't have enough voltage in order to operate. Or maybe it's internal short to ground or an internal open. And then, of course, we have resistance, right? We have the corrosion, the green fuzzy stuff that gets on all the connectors all the time, or actual physical damage, right? If I have that chafing wire again, it could rub through the wire, the braided wire, but maybe I have a few strands left that are making a connection, but it's not enough to flow sufficient amperage to operate the circuit. So that would be high resistance in that line because I only have a few strands of wire to carry my signal, right? So when we're looking for a component failure, we're thinking about something falling into one of those three buckets. We should keep that in mind as we're going through the different sensors and components here. So first off, let's talk about those thermistors. All right. So by and large, generally speaking, when you're going to run across one of these temperature sensors, could be a coolant temperature sensor, cylinder head temperature sensor, radiator outlet temperature sensors, all sorts of temperature sensors on a vehicle. You're going to have your connector up on the top, of course, and then inside you're going to have an element that will alter resistance based on temperature. So if we look at this simplified graph on the right-hand side, my temperature is here on the horizontal, and my resistance is going to be on the vertical. So as the temperature increases, the resistance will decrease. Right? And oftentimes a manufacturer will publish a table as to, well, at this temperature, it should be this resistance, and it should be this voltage, because the voltage output will change based on the resistance. And that's how the computer knows what the temperature the vehicle is. It can't see exactly, oh, it's 210 degrees. No, it sees X number of volts, which means it is around about 210 degrees, right? And they're not 100% accurate, but they're close enough where we could see that. Now, the problem you're going to have is could be a power supply issue, open, short, or it could be a signal issue getting back to the computer, right? So it's only a 2-wire sensor. Sometimes it's a 3-wire sensor, but oftentimes it's a 2-wire sensor. And the signal might just not get there, right? Could have a high input, low input, something of that nature. So for testing it, in this case, fairly simple procedure, right? So my coolant temperature sensor on this wiring diagram is right here. I have my signal wire on this line that goes back to the computer. And then I also have my voltage feed. Now, if we look at this, though, this is another important point I'd like to make. Just because it seems like it's a simple sensor doesn't mean it's necessarily the simplest electronics diagnostic. Because if we look at this line right here, this black and yellow line that's highlighted, that also feeds the MAP sensor. It also feeds the NOx sensor. It feeds the engine oil temperature sensor. And in this case, it's got tumble generator valves in the intake. So those actuators are also fed by the same signal wire. And that is a 5-volt reference signal from the computer. So if I have a bad coolant temperature sensor, or I get a code for a bad coolant temperature sensor, and I go to check for my voltage and I have 2 volts at my 5-volt reference, or I have 1 volt or half a volt, or whatever that's not 5 volts at my where I'm supposed to see 5 volts, well, it's not going to operate correctly anyways. It's not getting fed the proper voltage. So I'd want to take a look at this wiring diagram and see, well, what further down the line might there be a problem? So then maybe I'll check my MAP sensor and see if the 5-volt reference is low there. Probably get a code for that as well. Go back to my NOx sensor. Maybe that has low voltage. But over here, my engine oil temperature sensor, well, that voltage is good. So in that case, that might mean my break is somewhere in here, past this splice or somewhere in this neck of the woods. I'd have a problem, especially if my NOx sensor didn't have the voltage, right? So we want to start at the end, test it, and work our way backwards and see if we can figure it out. Right, so you maybe test the coolant temperature sensor first. If you don't see 5 volts there, check there's 5 volts coming out of the computer. If there is, then maybe you have an open somewhere in the line and you just check on down the line, see what the problem is. Seen that many times where one sensor could have an internal problem in the sensor, and it can be pulling the voltage out of the 5-volt circuit, and it pulls the rest of everything else out of whack. Right, so we want to make sure that when we're looking at it, we want to double check the wiring diagram as well. Like I said, it seems like simple, but it's not always the case. Could just be, yeah, it's bad, but could also be some other problem in the system. There's a few ways we can test these. So we have a voltage test, and then we also have a resistance test we could do. So this is just an example here of a voltage test. If the vehicle is at operating temperature, it should be 1 to 1.4 volts. In this case, we were a little low, so we were a little below operating temperature actually in this case. So we see that would have been okay according to where we were at. And then as far as your resistance, oftentimes you will get a temperature versus resistance table in there. So in this case, on this sensor at 32 degrees, it's 5.9 kilo ohms. Up to 176 degrees, you get 0.3 kilo ohms. and so on and so forth. So if it's less than that, the temperature's higher, and so on. So sometimes you get a little bit more of a table than this, but in this case, we get 4. All right, so we have the ECM ground and then the ECT signal as well. All right. Now let's talk about the thermostats. Those are our thermistors. Now we'll talk about our thermostat. So old school thermostat that we've been used to forever. They've been on cars for a long, long time. It's a fairly simple mechanical device. No electronics involved. So if we look on the left-hand side, that's just kind of a side view. We have our round circle that goes over the hole. And then we have our valve mechanism here, the spring. If we pull the cross section out, there's my little gasket. In this case, it's an O-ring. And then I have my valve here that opens and closes. And in here, we have wax. So you call that a wax element. So usually it's brass on the outside and the wax is on the inside. When the wax gets hot, due to touching hot coolant, it will melt, and then this valve will open and allows coolant to pass through. When it gets cooler and then the wax rehardens, it'll close back up and it'll close the hole. So it's not the most accurate thing in the world, and you can have a decent range of where it opens and closes, but that's what we've been using for years and years and years. It's just a simple mechanical device based on wax melting. So wouldn't you know it, a few years ago, manufacturers decided, well, let's improve on that. Let's improve on this simple device, and let's add a heater to it. So in this case, this is a electronic heated thermostat. And what they do is it's got basically power and ground. It's usually pulse width modulated, and it can heat up that wax using the heater element, and it'll heat it up before the coolant gets a chance to heat it up. So I can actually open it and run the engine cooler if I need to, or I can keep it closed longer and allow it to warm up faster because I could have a higher melting temperature on my wax, right? So it allows it to change when it's opening versus just waiting for that wax to melt. I'll make the wax melt, right? Now that's one way. That seems to be the most common way to see it out there. There are a few others that operate a valve, things of that nature, maybe just like a spool valve or something like that, to be able to bypass coolant as well. But by and large, what I've seen anyways is this heated thermostat, where there's a heated element over that wax pellet and allows it to open that way. So, we gotta complicate things by putting electronics on it, right? But I guess it makes it better fuel economy and all that good stuff that they're looking for, right? Here's just an example. This is on a Mercedes C series, and that's there's a lot going on here, right? So the actual heated thermostat element's over there, but it comes all as a big assembly with the captive bolts already there, and looks like it's got some quick connects on there, a couple of the hard lines already there. So that's simply just unplug it and plug the new one in, I guess. But there's your thermostat for this Mercedes, right? Kind of crazy to think about that. And it's also like $200. So it's not large, it's $300, closer to $300. So this just gives you a download. I went into Shopkey, not Shopkey, and got a component test. Got a component test on any of our tools that have a scope. You have this database of information in there, so it tells you how it works. So on this case, I'm looking up on 2012 BMW. Conventional wax thermostat is used with addition of a heater element. Thermostats will have a rated temperature, which they open to allow coolant flow to enter the engine radiator. During normal operation and low load conditions, the coolant circulates around the engine and the internal heater radiator, or the heater core. It's often referred to as a short coolant circuit. When the coolant temperature reaches the thermostat opening temperature, the wax will melt and expand. This opens the thermostat and allows coolant flow to the engine radiator. It's often referred to as the long coolant circuit. So during high load conditions, a greater cooling effect is required, so the engine control unit uses an electric current to flow through the heater element. So it'll open it up at a cooler temperature. Causes the wax to melt before the coolant reaches a high enough temperature to open a thermostat in a conventional way. When the current is switched off, the wax solidifies again, thermostat will close, and coolant will again only flow around the short circuit. All right, so the PCM controls the operation of the thermostat, opens and closes the thermostat via heating element located through the center of the thermostat's heat-sensitive spring. Then modulates the thermostat's heating element ground. More precise engine temperature control can take place. All right, so all of these things are the benefits. And then how am I going to test it? Well, you can test the pulse width, you can test the voltage on that as well. And we'll look a little bit deeper into some of these when we go live on the tool as well to see what the test would actually look like. But that's just one example, and there's quite a few cars that use this element now, not just Mercedes, BMW, but Chevy, Ford, that sort of thing as well. How about cooling fan? Cooling fan used to be pretty simple too, right? If we think about, the early cooling fans, they had the switch, the coolant temperature sensor would actually activate the relay to turn on the fan. Then we came into computer controls and the like. So in this case, on this vehicle, we have two cooling fans. One's the main fan motor it's used for cooling, and then the other one's used oftentimes when the air conditioner is on. So we need that extra cooling effect on the condenser there. So simply, the ECM has two controls, one for each fan. And when it does send it, it's going to ground the relay, right? Ground the coil in the relay, flips over, allows current to flow, and then it will go in and turn that motor. Now, on these conventional motors, though, you might be able to do something that you wouldn't necessarily think of before now. And how about current ramping a cooling fan? Now, you may have heard about us talking about current ramping a fuel pump before, and you current ramp coils and things, but current ramping a fuel pump is very similar to a cooling fan, except the cooling fan's structured a little bit differently. So here's just an example. Took it off a standard cooling fan with no control modules. So that's a really easy one when we have relays and things. And the difference between a cooling fan and a fuel pump is a fuel pump has fewer commutator segments in there. So most fuel pumps are going to have 8 commutator segments. In the case of this vehicle, and I've found it to be true on a lot of vehicles, is that's way more. So in this case, we have 20 commutator segments on this vehicle. They're a lot smaller and they're spread out over the course of the fan. So how do I know it has 20? Well, I took a look at the pattern and found out where does the pattern repeat. So we see we have this one notch that comes up, comes down. We got this little dip right there and it comes down. And then over here, we got the same thing with the little dip right there and it comes down, right? So I'll call that number 1. It doesn't really matter because it's a circle, but we'll call that number 1. So if I tag that, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 commutator segments before it repeats again. So I want to look at the condition of the commutator segments, make sure they're all pretty even, make sure there's not a lot of noise going on, make sure none of them are missing. If any of them are missing, that's a damaged fan motor that needs a replacement. If it's got a lot of noise in there, that's going to need a replacement, of course. I can also check RPM. In the same way, I can check an RPM on a fuel pump. So in this case, if I know there's 20 commutators, I'll put cursor 1 there, cursor 2 there, and take my time difference. So my time delta right here is the difference. That's the time it takes to get from number 1 to number 2. So that's 1 rotation we established, right? So that means 1 rotation on this goes 29.5 milliseconds is how long it takes. So I could do a little math, pull up my calculator. 60,000 milliseconds in a minute, divided by that 29.5, means it's turning at a little over 2,000 RPM. Sounds about right to me. Now, if I had a little tachometer gauge thing, I could check it and verify it, but more than likely that's correct. About 2,000 RPM. The math works out anyways. So that means it's going well. Now, if we're getting down to a couple hundred RPM and it's supposed to be on high, that's probably a problem. Oftentimes, I mean, it's pretty simple on a cooling fan, though. If it makes noise, it's probably got a shot bearing or something of that nature. But if you ever took one apart, you can see the brushes and the commutators and all that. And we can test it in the same way as any other electric motor. So I thought that was kind of a neat little thing to share with you. So that's on a standard cooling fan pump. Now we also have other cooling fan pumps, or actually cooling fan motors, that work in a similar way. Sometimes they can be pulse width modulated though, so that might not necessarily give you that current ramp. So here's an example. It's on a Ford Crown Vic, think like late 2010s or so, Crown Vic. And that one has an engine cooling fan module on it. So in this case, it's mounted right to the fan, and it has power. It's got ground, and then it has a variable speed signal that comes from the PCM. So the PCM, depending on, well, in this case, it's got the cylinder head temperature sensor, not a coolant temp sensor. So depending on what that sensor tells it, how hot it is, it's going to send a variable pulse width signal in here. And then judging on that, it will vary the speed of the fan. So we may have a module in the way as well. So you got to take that into consideration when you go into testing the circuit. All right, how about active grill shutters? You might think, oh, this is a body part, right? But where do they go and what do they actuate? Well, they cover up the grill, right? So here is a example, little animation of some active grill shutters on a truck. And look, it covers the whole radiator. So I can open them, I can close them. There's a little actuator and a little little arm in there and opens them and closes them, depending on how we want to have them open or closed. Can change the aerodynamic profile of the vehicle. Also changes the amount of airflow going through the radiator. So that is definitely part of my cooling system at this point nowadays. And it only used to be on a few cars. Now it's on pretty much all the cars that are out there. Most of your brand new cars are going to have some sort of an active grill shutter on there to take a look at. So definitely something to be diagnosing, looking forward to. So here's just an example. I think this is on a Ford, and it's behind the left side of the front fascia and the actuator. So we have a fuse, we got power, simple enough, right? Power and ground. On this vehicle, though, it is controlled over a LIN bus. So LIN stands for Local Interconnect Network. That is a low-speed data bus. So you'll actually see a data signal coming from the computer if you were to test it right there. So that is one of the options. And this is on a 2018 Ford Explorer. You can see we got the ground, LIN bus, and then power from the fuse. Active grill shutter uses a grill shutter assembly with a grill shutter actuator. The active grill shutter system is used to maximize fuel economy by reducing aerodynamic drag on the vehicle. So it'll close it so the wind goes over. Active grill shutter system shortens the engine warm-up time as well, because I'll close off the shutters, and then my radiator won't be getting as much airflow, right? Now it receives position commands from the PCM, and the grill shutter system carries out a calibration sequence whenever the engine is started. So it self-calibrates whenever it starts. It'll fully open and close the shutters before being positioned where it is told to position, right? So it's behind the dash there. So in this case, we have a LIN bus. Another case on another vehicle. This is, I think this one's a Chevy Cruze, if I remember. We're going to have voltage. We're going to have ground. And then in this case, the controller, it's got a logic board in the actuator. So really, this is just a variable pulse width signal coming from the computer in the case of this vehicle. So let's see. That is, it's Chevy Cruze, right? So it's a 2016 Chevy Cruze. And that one has a shutter control, which is variable pulse width, ground, and then the supply voltage on that vehicle as well. Now, I also wanted to note that I picked this page for a reason. Look for damage to the shutters from road debris or something stuck in the shutters, keeping them from opening or closing. And guess what? That'll set a code. Never would have thought that a pebble wedged in my grill shutter is going to set a code, but it can't. I actually remember seeing, I forget what kind of car it was on, but I remember seeing a TSB while doing this research that said, yeah, look for a rock. And sure enough, they had a picture of a pebble right inside, and it was keeping that actuator from opening. So yeah, just take a look, visually inspect. That could be the cause of the code, right? Crazy to think about. And our last component before we go live is we're going to talk about the electric water pump. Now, I know we're used to the normal mechanical water pumps, but to save on parasitic draw or parasitic drag on the engine, mechanical drag on the engine, some manufacturers have decided it's more efficient to go with an electric water pump, right? So in this case, this is off a BMW. You can see the connector right there where the power, ground, and such will go. And then we just have an inlet and an outlet. It's just a simple impeller there, and it just rotates the water. So in this example, it's on a 2012 BMW, and that was the picture we just showed there. It's used to precisely control engine temperatures. This will improve operating efficiency as well as promote cleaner emissions, which is better for everybody. It's controlled by what we call a BSD control signal. So BSD stands for bit serial data, and that is another low-speed data bus. Right, it's a single-wire data bus with a data transfer rate of 1.2 kilobaud. It'll request functions, identify data request information, as well as send component fault messages as required to the modules that need the information, right? So it has that right to the water pump, and that's what controls it. Bolts are aluminum, must be discarded, never reused. They're also a torque angle bolt. So tighten to 10 Newton meters and a torque angle of 90 degrees. So if I wanted to pull up the wiring diagram on this car, we can see we got power coming down from here, and then we have ground over here, and then we have our bit serial bus, which goes right there, right? So we have our bit serial bus signal, and it goes to the coolant pump and ramps it up and slows it down and controls it and changes it based on vehicle driving conditions and what's required. So if I were to test this, power, ground, and then the bit serial bus will actually take a look at what the signal is supposed to look like, but it's supposed to look like a square wave. All right, so we'll be able to see that as well. All right. There we go. So let's go to a live walkthrough here. and we're going to pop up our Zeus here. All right, so let's go through a couple different vehicles, a couple different ways we can test things, and where can we get more information here. So let's go into guided component test first. So if you have a Snap-on tool that has a scope, it will have guided component test in there. And that is a database that goes back to 1981, covers dozens of different vehicle manufacturers. You can see them all on the screen here. But before I ID a vehicle, because it is VIN-specific information, we can also go into training and classes. There are hundreds of built-in training and classes inside the tool. And there's a specific one that talks about what we're talking about tonight. So if I go in here and go to how to, 65 different categories of classes in here. One that pertains to what we were just talking about is LIN bus, right? I talked about local interconnect network, and that is the low-speed bus that we might use on some of these. But the one that I want to talk about is in here somewhere. There we go, 15-minute mapped cooling system class. So when we're talking about these electronically controlled thermostats, we're also talking about mapped cooling systems. So some vehicle manufacturers are now using a mapped cooling system. By electronically controlling the thermostat, the engine management system can allow coolant flow through the engine radiator at a lower coolant temperature. The thermostat with a higher operating temperature can also be fitted. So this allows the engine to warm up quickly and run at a higher temperature when required. And then it gives you a rundown of a couple different methods. So we have both the electrically heated thermostat, which we talked about, and then the other, I think, less common one is going to be a solenoid bypass type thermostat as well. So those are both in there. And they both still use the wax element. It's just they use it in a different way. So you can actually go through, read through that on the tool if you wish to do so. All right, so let's exit out of here. And now let's pull up one of my vehicles, and we'll talk about a few different things we can do here. So let's go in and check that Chevy Cruze first. I think that might be where that TSB was. So we go into a Chevy Cruze. I'm going to go into my shop key. Let's call it an LT. Okay, come in here. It's going to load my vehicle for me. Now I'll say it's an LS. What the hell, right? Gas, automatic, uses vehicle. Okay. Chevy Cruze, fairly common car, right? So let me pull up my active grill shutter. That up, see what we get for information here. All right, so we get our specs, our testing, guided component testing, remove and replace. All right, so if I go into remove and replace, visual and physical inspection, inspect for aftermarket devices, and inspect easily accessible visual system components. Also look for rocks, broken things. All right, so we have that in there. Wiring diagrams, we can go in and we can see how we would test that. So I can pull that up to my engine performance system, circuit 2 of 7. Once I open my wiring diagram, you'll see it's pre-highlighted and dim all the wires around it. And then I can see where it goes over here. So we got power, just going to go to a fuse, right? There's my fuse block. And then my ECM is going to be over here. It's going to bring me all the way over and bring me over to my ECM as well. So it's going to help us with testing. We also have guided component testing we can do on this. So if I go into guided component tests, load my Chevy Cruze there, go into engine. And we have active grill shutter test right there as well. So we can go to component information, tells us how it works. We already actually read through this on the slides, but I could do a DC voltage test. All right, it's going to tell me the voltage is going to toggle on and off with the chassis control module commands the shutters to move. So we'll see a positive and negative alternating voltage, not alternating, the DC voltage going back and forth, power to ground. All right, so we have a couple tests we can do there. Let's go back to a couple other components, see what else we have on here. In this case, on this vehicle, we also have a heated thermostat. So like I said, it's not just on BMW and Mercedes. It's also on the Chevy Cruze right here. We have a heated thermostat. So it's going to tell us how it works. Through the center of the thermostat's heat-sensitive spring modulates the thermostat. So we can do a duty cycle test. It's going to tell us should command the duty cycle to 0 and hold engine RPM. Coolant temp should increase greater than 215 degrees. Temperature should decrease as duty cycle is increased. So we can duty cycle it up and down using a functional test. Signature test. It's going to be a square wave. All right, as we said, it's a modulated signal, so you're going to see up and down, and the frequency will change over time depending on what my pulse width is. And then an outer range of signal test is there as well. We're going to measure power and ground. So that is heated thermostat. Let's go into my BMW. Tried and true BMW. Guided component tests, engine, and let's go to the water pump, because this was the interesting one with the bit serial data line, right? So I can go into component information. It's going to tell me how it works. We already looked at that. But if I back up and go to my signature test, it's going to show me what my serial data should look like. So it's going to look like this. So it's not the actual control signal. It's actually the data bus, the bits and bytes, the ones and zeros that are going back and forth on the signal there, right? So we can have our ons and offs, our ones and zeros, very easy to test. And then we can just take a look at the signal and make sure we have that square wave as well. And it also says a good way to test this is there's an automated bleed procedure that takes 12 minutes on the car. And what it does is it cycles that pump for 12 minutes. So that gives me plenty of time to test it while it's doing that. So that's just one suggestion on how to do it easy enough. You can also do a functional test to turn it on and off to test it that way as well, right? So lots of information available in there in the guided component test. Also lots of information available in my ShopKey or other repair information system. Plenty of information there. There's also functional tests we can do to cycle things on and off. So definitely a lot that we can do. And I think that's probably a lot more than you may have thought was going to be contained in the coolant system as far as electrical components, right? So I know I definitely learned a lot about some of the newer technology research in this one as well. So hopefully you learned a lot too. And with that, that is our time here today. So make sure you tune in for new diagnostic content every week. We will be premiering a new video every Wednesday at 7 p.m. UK time. So make sure you check it out on the YouTube channel. If you're watching, well, of course, you would be watching this on YouTube, but make sure you subscribe, thumbs up, ring the little notification bell so you know anytime we post new content. And it's youtube.com/SnapOnDiagnosticsUK. With that, time for questions. If you have any questions, just feel free. Once again, if you're watching this on a premiere, just leave it in the live chat and we'll answer those. Otherwise, leave a comment under the video and we will get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've given you today. Hopefully we'll see you next week. Hopefully you can watch and see you on any of our other videos. Have a good week, have a good night, and take care.